Good day, learners. Welcome back to our chemistry class. In today's class, we are going to continue on our electrolysis. If you have not watched the previous video, kindly do well to click the link in the description box. Now, electrolysis was brought about by a man, a scientist called Michael Faraday. Michael Faraday proposed two laws on electrolytic processes, which we know as the first and second laws of electrolysis. Now, before we now dive into this properly, if you're a new member on this channel, kindly subscribe to my channel and click the notification bell for my subsequent content. And don't forget to share and like as we move on. Now, let's proceed. Faraday's first law of electrolysis. Faraday's first law of electrolysis states that the mass of elements deposited or liberated during an electrolysis is directly proportional to the quantity of electricity passing through the electrolytes. That is, the mass of the elements that's going to be deposited or liberated. Sometimes they will say discharge. The word discharge is a single word used to mean deposited or liberated. When something is being deposited, it goes down the vessel or the container. Like when you pour sand in water, the sand will go down. Why? Because it is solid. They are solid. So they are going to be deposited. They move down. But in terms of gases, they are going to be evolved. They liberate. So that is liberated. The mass of the element deposited is directly proportional to the quantity of electricity passing through it. That is, if we could recall from our physics, we should recall that Q, quantity of electricity, is equals to IT, where our I means the current and T is a time taken. So the current that is being passed through the electrolytes and the time taken for the mass of the element to be deposited. So when you input this one, we have M is proportional to IT. Remove this proportionality, we put a constant. M is equal to ZIT, where this Z means electrolytic equivalence. Now, our Z can be equal to mass over IT, where mass is gram and IT, which is the quantity of electricity, that is Q, is in coulombs. Then the inverse of this, 1 over Z, will equal to IT over M, where this one is a constant, as we know, a constant, and the unit of it here, the unit of this IT is Q, that is coulomb over what? Gram. Coulomb per gram. So this will be useful as we move on in our discussion. Now, from here now, we can now see that from the interpretation, when the mass of the element deposited is increasing, the current passing through the electrolyte will also be increasing. Meaning, the higher the current, the higher the mass of the element deposited. From here, we now plot a graph of mass against current. It must give us a straight line. Meaning, as you are moving up, as the mass increases from 1, 2, 3, 4, the current also will also be increasing. The current will be increasing as the mass increases. It will be increasing like that. So the higher the current of the electricity passing through the electrolyte, the higher the mass of the element that is going to be what? Deposited or liberated during the electrolysis. Now, from this formula, Q is equal to IT, we can get some calculation here. So let's proceed. Example 1. A current of 0.72 amperes was passed through a solution of an electrolyte for 3 hours 20 minutes. Calculate the quantity of electricity passed. Now, a current of 0.72 ampere. Current is I, as we have done. 0.72 amperes was passed through a solution of an electrolyte for 3 hours 20 minutes. Our time there is 3 hours 20 minutes. Now, one thing we have to note is here, our time must be in seconds. So this will be converted to seconds. So 3 hours will be converted to seconds. 3 multiplied by 60 times 60. Then plus 20 minutes will be converted to seconds. 20 multiplied by 60. Now we multiply this. What do we have? Here we have 10,800 plus 2 times. So this one we have 1,200. So when you sum it up, we have 12,000 seconds. Now recall that Q is equal to IT. So when we are asked to calculate the quantity of electricity, so our I is 0.72 multiplied by our time is 12,000 seconds. So let us multiply. We have 8,640. So the unit of Q is coulomb. Example 2. When a current of 0.20 amperes was passed through an electrolyte, 1,200 coulombs of electricity was used. Calculate the time of current flow. Now, when the current, our current I is equal to 0.20 amperes, was passed through an electrolyte, 1,200 coulomb. Coulomb means Q. Q equals to 1,200 coulomb. Then calculate the time of current flow. Now, we want to find the time unknown, and don't forget that Q is equal to IT. Our Q here is 1,200 is equal to our I, 0.20 multiplied by time. I need my time. I have to divide both sides by 0.2. 1,200 divided by 0.20 equals to 0.20 times t over 0.20. This cancels this. My t equals to 0. Let us divide. Our time here is 6,000 and the unit is what? Seconds. So this is how to make use of the Q equals to IT. Faraday, the mole to mass relationship. Now, in theory, the quantity of electricity passing through an electrolyte is always equivalent to 96500 coulomb. And this 96500 coulomb is referred to as Faraday's constant, which means 1 Faraday is equivalent, that is equals to 96500 coulomb. And this 96500 coulomb is equivalent to 1 mole of any elements. 1 mole of any elements in the electrolysis. Likewise, it's also equivalent to 6.02 times 10 raised to the power 23, which is what? Avogadro's constant. Which is the Avogadro's constant. So which means that for any element, 1 mole of that element will be equal to 96500 coulomb, which is 1 Faraday. Then that 1 mole of that element as well is also equal to an Avogadro's constant, which is 6.02 times 10 raised to the power 23. Now from here, we can now look at all these elements. We have some monovalent elements, divalent elements, trivalent elements, and so on like that. Let's say, for instance, for the monovalent elements, like sodium ion, This sodium ion is going to accept one electron to be deposited as sodium metals. From here, we have one charge here. That the charge here is 1. Likewise here. So we mean 1 Faraday. This 1 Faraday here equals to what? 1 mole. So which means that the number of mole of sodium elements here is going to be equal to 1 Faraday, which is what? 96500. So this is 96500 coulomb is equivalent to 1 mole. Likewise, this 1 mole also is equal to the molar mass of this sodium, which is what? 23 grams per mole, or 23 grams. Now, let's say we have divalent elements like lead, Pb2 plus. When it accepts 2 electrons, it's going to be deposited as Pb, as our solid. So this one now is 2 Faradays of electricity. We'll be depositing 1 mole of lead. 1 mole of lead. It's balanced like this. Plus 2 minus 2 give us 0. And the oxidation number of lead here is 0. So, but this one is 2 multiplied by 96500 coulomb, which is going to be equals to 1 mole. And this 1 mole of lead is 207 grams. So that is the mass to mole relationship we are talking about. Now, for aluminium 3 plus is accepting 3 electrons to be deposited as aluminium. Now this is now 3 Faradays of aluminium is giving us 1 mole of aluminium. Fine. Then this means 3 multiplied by 96500 coulomb giving us 1 mole. And 1 mole of aluminium equals to 27 grams. So these are for the cations. What are for the anions that are negatively charged? Okay, let's for chlorine. Chlorine, that is chloride ion. Chloride ion is going to, instead of gaining, it's going to lose. Here, it's going to give us chlorine plus 1 electron. But we know very well that chlorine is a diatomic gas, meaning it can never be written this way. It should be Cl2. Now, if I put 2 here, Cl2, definitely 2 will be here. Then I'm going to have 2 here. This means 2 Faraday of electricity here is going to deposit 1 mole of chlorine. 1 mole of chlorine. And in terms of mass, it's going to be, so 1 mole of chlorine will be, chlorine is 35.5 multiplied by 2. While this one will be 2 multiplied by 96500 coulomb. So that is 71 will give us this. That is for the chlorine. Now also for oxygen. Oxygen is O2 minus moving to O2 plus 2 electrons. This is the normal way we're supposed to have oxygen. But oxygen is not like this. Oxygen, during the electrolysis of acidified water, oxygen was gotten from OH minus. From OH minus. This OH minus produces O2 plus H2O and electrons. Now we want to balance this. To balance this, 4 of this OH minus is going to give us this. So here we are going to have 4 electrons here, since this one is 4. So definitely our oxygen must be 4. So let me put 2 here. Oxygen here is 2 plus 2 making 4. Hydrogen is 4, hydrogen is 4. From here now, 4 Faradays of electricity is going to give us 1 mole of oxygen gas. That is, oxygen, that is 16 multiplied by 2 grams, will give us 4 multiplied by 96500 coulomb. Now, this one is wrong. It can never be used. Instead, during the electrolysis concerning oxygen, oxygen must be gotten from OH minus, and which is giving us 4 Faradays. Example 3. Calculate the amount in moles of aluminium that will be deposited by passing 4 Faradays of electricity through a solution of an aluminium salt. Now, we're talking about aluminium. We know aluminium to have 3 charge, to accept 3 electrons, and be deposited as Al, aluminium. From here, we have 3 Faradays of aluminium. It's going to deposit 1 mole of aluminium. Now, from this relation, we can get our answer. Calculate the amount in moles of aluminium that will be deposited by 4 Faradays of electricity. If 3 Faradays of aluminium ion deposit 1 mole of aluminium metal, then 4 Faradays of electricity. Faradays must be under Faradays. 4 Faradays of this aluminium ion will now deposit how much? Let's call it an unknown y. Cross multiply. We have 3F, 3 Faraday times y is equals to 4 Faraday multiplied by 1 mole. We need our y. We have to divide both sides by 3F. 3 Faradays times y over 3 Faraday is equals to 4 Faradays times 1 over 3 Faradays. This cancels this, y equals to F cancel F. So 4 divided by 1, 4 divided by 3, so we're going to have 1.33. So it's under mole, that is mole. So which means that 4 Faraday of electricity is going to give us 1.33 mole. Example 4. What quantity of electricity will liberate 0.125 mole of oxygen gas during the electrolysis of dilute sodium chloride solution? Now, given that 1 Faraday equals to 96500 coulomb per mole, don't forget we are dealing with oxygen. Oxygen was derived from OH group minus, which is going to give us oxygen plus H2O plus electron. And this is going to be 4 Faradays, and this one will be 2. So which means from here, 1 mole of this oxygen will give us 4 Faradays. And we are told that 1 Faraday equals to 96500. That is, 1 mole of oxygen gas is going to produce 4 multiplied by, this F is 96500, then in column. Then 0.125 mole of oxygen given to us will now deposit how much? That is unknown. Let's cross multiply. 1 times x, I have x equals to 0.125 multiplied by 4 multiplied by 96500. So what do we have? So we are going to have 48,250 coulomb. So which means that for us to produce 0.125 mole of oxygen, it required 48,250 coulomb of electricity. So this is some of the questions related to the first law of electrolysis. We are just starting. We are going to look at the second class in the Faraday's first law of electrolysis till we finish it and move on to the second law. If you are a new member on this channel and you find this class so interesting, kindly subscribe to my channel and click the notification bell, and don't forget to share and like. Thank you very much.